This video deals with formal charge and Lewis structures. This video again follows along with the Word document kind of on that second page or that back side of that dealing with formal charge. What formal charge is formal charge is a way to write even better Lewis structures. And we're going to use formal charge as a way to breaking what seems like a tie between two very, very comparable Lewis structures in order to figure out which one is the true structure, which one is the better structure to try to represent the molecule. So the first thing we want to talk about with formal charge is when we say formal charge, we want to think about formal in the formality sense, not in the course of like fancy clothes type sense. It's a formality of calculating a charge. This formal charge is not a real charge. It's kind of a little bit of an artificial, just accounting purposes, but we can use this as a tool in order to write better Lewis structures. So before I can show you how we can use that to break a tie, I first have to show you how to count formal charge for a molecule. So what I want to do is I want to do a couple molecules that we've already dealt with. One of the molecules we've already dealt with is NF3. You've already written the Lewis structure for this. So if you want, pause the video right now and practice writing out this Lewis structure, because I'm going to kind of skip right to that actual Lewis structure. So for NF3, we had this as our Lewis structure. Again, here's a good chance to pause it, make sure you're able to write this out for yourself. So here is our Lewis structure that we ended up with for NF3. So we're going to use this as an example of how to count formal charge. So what formal charge is kind of a balance between the formal electrons and the valence electrons. It's a comparative of those two. So what formal means is every electron in this structure we're going to formally assign to a specific atom. And then we're going to compare that to how many actual valence electrons it had. So let's look at this fluorine. If I formally assign electrons to this fluorine, certainly the lone pairs belong to fluorine. 2, 4, 6. They're definitely owned by fluorine. This bond, remember this bond really has 2 electrons. Anytime you have a bond, you want to formally assign one of the electrons to each atom of that bond. So these 2 electrons, we're going to formally assign one to the fluorine, one to the nitrogen. That's going to give fluorine 2, 4, 6, and one from the bond, 7 formal electrons. Those 7 formal electrons match with the valence electrons from fluorine. So since they match, we say that fluorine has a formal charge of 0. If we go through the rest of the elements in that same way, this fluorine is going to behave the same way. 2, 4, 6 belong to the fluorine for sure. One of these 2 from the bond makes 7. 7 formal electrons for this fluorine. That matches the valence electrons. We would call that a formal charge of 0. Fluorine on the right, again, 2, 4, 6, the lone pairs definitely belong to the fluorine. Get our lone pair in on the nitrogen. 2, 4, 6, we definitely have 6 belonging to the fluorine. 1 from the bond makes 7. Again, that matches our valence electrons. Formal charge of 0. Now we correctly made sure we got that lone pair in on the nitrogen. We're going to do the same thing for the nitrogen. These 2, 1, 2, definitely belong to the nitrogen. Nitrogen also gets 1 formally from each of the bonds. So 2 already, 3, 4, 5. That matches those 5 formal electrons here match the 5 valence electrons here. That's going to give us a formal charge on the nitrogen of 0. I want to do another example of calculating formal charge because they won't always come out to be 0. I want to use an example where you're going to see some pluses and negatives for this. And I'm going to pick one that we've also have already looked at. One of the ones that we've already looked at is SO2. For this, even though this has resonance structures, we just need to look at one single resonance structure in order to do formal charge. Again, feel free to stop the video, try to draw this out for yourself. We would end up with something like this. For our Lewis structure for SO2. And remember, it doesn't matter which resonance structure you draw, we just have to look at one of them in order to do formal charge. So I'm going to do formal charge on this the same way we did previously. I'm going to assign formal electrons to each of the atoms, and then we're going to compare it to how many valence electrons it brought into the mix. So this oxygen on the left, lone pairs, 2, 4, those definitely formally have to belong to the oxygen. Oxygen's also going to get formally assigned 1 from each of the bonds. So 2, 4 from the lone pairs, 5, 6. This oxygen on the left has 6 formal electrons. That matches the number of valence electrons. So this one still has a formal charge of 0. Let's look at the oxygen on the right though. 2, 4, 6. 6 formal electrons from the lone pairs. But remember, I also have the bond. In the bond, you split the electrons. One formally gets assigned to each atom from the bond. So one goes to sulfur, one goes to oxygen. So this oxygen on the right, 2, 4, 6, one from the bond makes 7 formal electrons. We're going to compare that to the number of valence electrons. Oxygen had 6 valence electrons, but in the structure, it has 7 formal electrons. It has 1 more formal electrons than valence electrons. So if we think about electrons having a negative charge, 7 formal electrons versus 6 valence electrons, that's going to give you that -1 formal charge on that oxygen. Remember, formal charge is always valence electrons minus formal electrons. Let's do it for the sulfur. We're going to assign formal electrons for the sulfur. 2 from the lone pair, and then 1 from each of the bonds. So 2, 3, 4, 5 formal electrons. Now we're going to compare that to the number of valence electrons sulfur had. Sulfur had 6 valence electrons. 5 formal electrons. So going from 6 valence electrons to 5 formal electrons, that's 1 less electron. It lost an electron. If we think about electrons being negatively charged, we would assign sulfur a +1 formal charge. It has 1 less formal electron than valence electron. So you need to think about electrons being negatively charged, or you're kind of looking at the idea of valence minus formal. So you won't always get zeros for this. So here, all I've done in these first 2 examples is assign formal charge to each of the atoms. What we're going to do next is we're going to go one step further. We're going to see how formal charge can be used as a tiebreaker between 2 very, very comparable structures. So that's what we want to work on next. And there's a set of criteria for dealing with formal charge that's kind of found on your worksheet. Generally, structures that have less formal charge, and by less I don't mean more negative, I mean closer to 0, less formal charge is usually better. That's one of the criteria. Usually you're going to stay away from things that have +2, -2, +3, -3 formal charges. Any big formal charges kind of isn't out there either. The other thing that you're going to see is that the sum of all of the formal charges will equal the actual overall charge that something has. You've seen that in the previous examples already. The NF3, everything was 0. NF3 has a charge of 0. For what we just did, the SO2, at a 0, a plus, and a negative, those would all add up to be 0. SO2 is not a charged molecule, that's going to match that. So here, I want to show you how to use formal charge to write better Lewis structures. First example I want to do is CO2. So if you want, pause the video, try to write out CO2 for yourself. Carbons in group 4A for 4, oxygens in group 6A for 6. We're looking at a sum total of 16 valence electrons. Now there's potentially two different ways you could have written out CO2. I want to go all the way to kind of the end to show you those two ways. So one option is you could have written this for CO2. But there's another option. You could have written maybe something like this. So let's compare and analyze these two different options you could have for writing CO2. Remember, there's kind of a third option that would just be the mirror image of this, where you'd have the triple bond on one side and the single bond on the other. But let's compare all these. The first thing we're going to do is look at these two structures without thinking about formal charge at all. Just making sure we have the correct total number of electrons and that we're following the octet rule. 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. That's good. Octet rule. 2, 4, 6, 8. Good. 2, 4, 6, 8. Good. 2, 4, 6, 8. Good. Following the octet rule, I have the correct number. That looks good. But what if I do the same thing down here on the bottom structure? Bottom structure has 2, 4, 6, 8, 10, 12, 14, 16 electrons. It also is going to follow the octet rule for everything. This oxygen, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. The carbon, 2, 4, 6, 8. Here's what I mean by we're in a tie scenario. So far, there's nothing to differentiate these two structures from each other in terms of which one's kind of more proper, which one's more appropriate for this molecule. This is where formal charge can kind of kick in and help us out with that. So I'm going to go through and I'm going to assign formal charge for all the atoms here, and then we're going to have formal charge help us break that tie. And that's all you ever want to really do with formal charge, is help you to break a tie with it between two competing structures. So this oxygen, formal electrons, 2, 4, 1 from each of the bonds, 5, 6, 6 formal electrons, 6 valence electrons, that's a formal charge of 0. Oxygen on the right, 2, 4, 1 from each of the bonds, 5, 6, 6 formal electrons, 6 valence electrons, that's going to be a formal charge of 0. Carbon doesn't have any lone pairs, but it gets formally assigned 1 from each of the bonds. 1, 2, 3, 4. 4 formal electrons match the 4 valence electrons. They'll have a formal charge of 0. Bottom structure now. This oxygen, 2, 4, 6, 1 from the bond makes 7 formal electrons. 6 valence electrons, though, gives us a formal charge of -1. Oxygen on the right, 2, and then 1 from each of the bonds, 3, 4, 5. 5 formal electrons compared to 6 valence electrons makes a formal charge of +1. The central carbon, no lone pairs, but 1 from each of the bonds, 1, 2, 3, 4. That's going to match our valence electrons, formal charge is 0. So here, even though the octet rule was kind of tied for this, they both had the correct number, formal charge predicts which one is the true structure. Generally, we want to pick the one that has the less formal charge. This has no formal charge on any of the atoms. Here we're dealing with formal charge. That's how we're going to eliminate the bottom structure as the structure, and our real correct structure is going to be the top one. Generally, when you have two competing structures, the one with the less formal charge is going to win out over the one that actually has formal charge on things. So that's how you can use formal charge to help break a tie. So I want to do another formal charge example, how you can help use this to break a tie. The example I want to do is BF3. So BF3, we would have 1 boron, 3 fluorines. Boron's in group 3A, fluorine is in group 7A for a sum total of 24. We'd start with the central atom, make the fluorines the outer atoms, complete an octet on those outer atoms. That means 3 lone pairs on each fluorine. Stop and see how you've done. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 24. Now you're checking for the octet rule. 2, 4, 6, 8 on the fluorine. Fluorine 2, 4, 6, 8. Fluorine 2, 4, 6, 8. Boron 2, 4, 6. So right now you're kind of at a little bit of a quandary. You're used to, whenever something doesn't have an octet, taking one of those lone pairs. If you don't have an octet in the central atom before, you've been kind of throwing those lone pairs in to make a double bond so it satisfies the octet. So you might be tempted to do that, but another part of you is going to say, gee, I'm looking at boron on the periodic table. It's in group 3A. I know things in group 3A don't necessarily have to follow the octet rule. So you're kind of at a quandary of what to do. You can kind of see pluses and minuses to doing both things. Well, let's explore those two different options and see if we can use formal charge to help us out. Well, let's say you did move those in, and you would get a structure like this on the bottom. So now you're kind of looking at this bottom structure, and you could have had different resonance structures if you used a different fluorine for the multiple bond. But here, let's just look at one of these potential structures. Let's analyze this the same way. Well, 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's good. Octet, 2, 4, 6, 8. That's good. Octet 2, 4, 6, 8. That's good. Octet 2, 4, 6, 8. That's good. Boron 2, 4, 6, 8. That looks good. So we kind of look at this and we say, gee, maybe we're leaning a little bit towards the bottom, following the octet with this. Because on the top, I'm not following the octet, even though boron doesn't have to. So we're kind of looking at this, but there's definitely still some question in here which one we're going to pick. You know, there's certainly some things going for the bottom structure. I'm following octets. But I know I might not necessarily have to have an octet on boron. Can we use formal charge here to kind of help break that tie? Or help us push one way or another for either this top structure or this bottom structure? Well, let's go ahead and count out formal charge for everything and use that to kind of analyze this. The top, fluorine, has 7 formal electrons. 2, 4, 6, 1 from the bond makes 7. That matches the valence electrons. That fluorine would have a formal charge of 0. This fluorine, 2, 4, 6, 1 from the bond 7. That's 7 formal electrons, matches 7 valence electrons, formal charge of 0. Fluorine on the right, 2, 4, 6, 1 from the bond makes 7 formal electrons. It matches the valence electrons, formal charge of 0. The boron, 1, 2, 3, no lone pairs, but it gets 1 from each of the bonds. 1, 2, 3, that matches the valence electrons. That's 0. Now let's do the bottom structure. Fluorine, 2, 4, 5, 6 valence electrons, 6 formal electrons, 7 valence electrons. So 2, 4, 5, 6 formal electrons, compare that to 7 valence electrons. That's 1 less formal electron for a formal charge of +1. this fluorine, 2, 4, 6, 1 from the bond, 7 formal electrons matches the valence, or formal charge of 0. Fluorine on the right, 2, 4, 6, and 1 from the bond makes 7 formal electrons, matches the valence electrons for 0. Boron has no lone pairs, but it gets 1 from each of the bonds. 1, 2, 3, 4 formal electrons. Compare that to the 3 valence electrons. 1 more formal electron than valence electron makes for a formal charge of -1. So now let's kind of analyze the two structures again. Well, what's going on? Well, top structure, I have no formal charge, but I don't have an octet. Bottom structure, I have formal charge, but I do have the octet. So far, formal charge hasn't quite done enough in order to fully differentiate between these two. This is where that third criteria comes in for formal charge. Here we're looking at having formal charge be consistent with electronegativity values. And what does that mean? For formal charge to be consistent with electronegativity values, that means it should match. Things that are more electronegative should have more negative formal charges. Things that are less electronegative should have more positive formal charges. So take a moment and look at a periodic table right now. Pause the video if you need to. Look at a periodic table right now. Look at boron versus fluorine. Which one of those two is more electronegative, boron or fluorine? After you've looked at a periodic table, you should be able to say, hey, fluorine's to the right of boron, it's more electronegative. Fluorine's also our most electronegative element. So right away, fluorine's our most electronegative element. It should have the most negative formal charge. So does our structure on the bottom match that? No. Our structure on the bottom is inconsistent with that. It's the opposite of that. If we had boron and fluorine having formal charge, just based upon what we know has to be true about electronegativity, we would want the fluorine to have the negative and the boron to have the positive. We have the reverse. So this is the final nail in the coffin for this bottom structure. Even though it has the octet, which top doesn't, so that's a plus for the bottom, even though this has the octet, it also has formal charge, and the formal charge does not make any sense with the electronegativity. It's not consistent with that. So that's the final nail in the coffin for this bottom structure. We're really going to be looking at the top structure as our true structure, even though it doesn't have the octet. The fact that it has no formal charge, and if we tried to give boron its octet, we get formal charge 1, and 2, it's formal charge that doesn't make any sense. Another way of kind of looking at it is you would start with the top structure anyway, but you'd be tempted to bring these in to make this bottom structure. So here's another way of thinking about it that could help lead you towards this top structure. Fluorine is the most electronegative element. That means it's the meanest, greediest element out there. It wants the electrons way more than anybody else. Is fluorine going to voluntarily share something that it already has exclusive ownership of with something else, unless there's absolute necessity? No. There's no absolute necessity to have that octet on boron, so fluorine's going to keep these. And the formal charge, the fact that we have formal charge, as well as the formal charge does not match up with our electronegativity, basically says no way are we going to have that bottom structure. Instead, we're going to have this top structure instead. So when you're thinking about formal charge, think about using it as a tiebreaker, as a way of comparing two different structures to each other, and use it in a way to push you away from one and towards another. One important thing about dealing with formal charge is don't overdo formal charge. I've seen people get so stressed out about formal charge, they start doing all sorts of weird, strange, illegal, immoral things on Lewis structures trying to make formal charge equal 0. Sometimes you're going to have formal charge, and that's okay. You just want to make sure that formal charge makes sense and is consistent with some of the other things you know have to be true. So don't overdo the formal charge. Think about formal charge as that last tie-breaking opportunity. When you really have two structures that you're considering and you're trying to say, which one am I really going to pick here? That's when you want to invoke formal charge.